Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome a speaker who not only is on site, but actually traveled away from Budapest to Warsaw, because it's difficult to take someone for dinner on Zoom. Anyway, we're very happy to have today GÁBOR ETESI from Budapest, and he will tell us everything and more about operator algebraic characterization of the vacuum Einstein equation in 4 dimensions. It's all yours. Take it away.
Thank you very much. So first of all, I'd like to thank for the organizers for this very kind invitation. First of all, to Piotr, and on the other hand, also the other organizers who might have been involved in this invitation. So I hope I will, fulfill this very high level of this seminar. And also I want to make still some initial comment that it is. I will talk about some functionalism, operator algebraic characterization of the Einstein equation. So it is some sort of intersection of operator algebra and functionalism and gravity theory. And also from this viewpoint, very lucky being in Poland, because we know that the gravitational research due to Leopold Infeld and Trautmann and many others also very strongly present here, and not to mention about functionalism, Banach and others. So thank you very much. So the plan is the following. First, I give a rapid introduction to this very diverse topic, so I will just focus on some few introductory parts and also present the main results. So these are 3 theorems whose proof I would like to just outline in this talk. So all technical details will be suppressed, and of course I am very ready to discuss about it later if somebody interested. So these 3 theorems are about the following points. So first, I would like to construct a von Neumann algebra in a very natural functorial way associated to any 4-dimensional smooth manifold. Then some sort of Neumann algebra dynamical system characterization of the Einstein vacuum equations in this setup. And also I would like to mention, but this part will be suppressed in this talk, how to use this construction to obtain some new smooth 4-manifold invariant. And finally, I would like to take a look or have some outlook toward physics, and I would like to compare the various representations of the 2 type 1 Neumann algebra from a physical viewpoint, and somehow mention about quantum gravity, whatever it means. Okay, so first, let me give some motivation. So physically, we know that already it is more than 100-year-old story that somehow the quantum field theory and the gravity cannot be unified. And it has infinite literature. Why? And also, maybe we can divide the problem at least in 2 parts. There are certainly some technical mathematical problems behind it, and also some deep physical conceptual questions. Why? And if we now focus on the pure mathematical and technical level, then there was a very interesting remark by Roger Penrose in the 70s that at least technically a very deep difference between general relativity and quantum theory is that quantum theory is inherently linear theory and based on the complex number. Somehow the wave function must be a complex number because of some reason. Meanwhile, general relativity is completely in the opposite end. So general relativity is a deeply nonlinear theory because the Einstein equation it contains the self-interaction of gravity, which cannot be separated from the gravitational field itself, and also deeply real theory. So the Einstein equation somehow doesn't show any hint that it wants to be reformulated in terms of complex number. So
may I remark that Roger Penrose is known for saying that it's not gravity that should be quantized, it's quantum theory that should be gravitized.
yes. So we know this famous debate between Hawking and Penrose. I don't know which side I am standing. That's a difficult question. Penrose
thing to discover. Penrose himself added complex numbers to general relativity.
This is what I want to mention here.
Right.
So Penrose's suggestion to bridge this technical gap was the twistor theory. So now I will not talk about this at all, but somehow we managed to replace the 4-dimensional real framework with a 6 real dimensional framework, which is actually a 3 complex dimensional framework. And now in this way he could introduce complex numbers into general relativity. So he says that this story is still somehow developing story. So anyway, this is just a comment. And also I would like to mention very, very briefly a mathematical motivation. Now it turned out after, I don't know, 50, again, half century of struggling, that the interaction of smooth structures or manifolds and the topology, underlying topology, is especially complicated in 4 dimensions because of some deep reasons. Somehow all successful higher dimensional topological methods to approach such questions breaks down somehow in 4 dimensions. Meanwhile, they also work in lower dimensions, 1, 2, 3 dimensions. And
related to downloads on exotic structures.
Yes, exactly. And here also theoretical physics have mathematicians to Donaldson and the Seibert-Witten theory to introduce new effective invariant, especially in 4 dimensions. And this led to the discovery of exotic smoothness even over the normal R4. It contains infinitely many non-differentiable structures which are not equal to the standard structure. And also in this, if Young's theory is so successful in 4 dimensions, we can raise why general relativity doesn't help it. General relativity has the same deep physical content, and why we cannot use it to understand the smoothness in 4 dimensions. It in principle could help because anyway, so this is also a motivating question. And here we will do something different. I will try to use the very advanced tools of operator algebra theory to find smooth invariants in 4 dimensions. This is not a hopeless task because we already know from Jones' polynomial theory that in the non-polynomial theory that operator algebras can help in topological questions. Okay, so these are the motivations to develop some operator algebraic approach to these questions here. So I will talk about this. So now I summarize the results. So I will outline 3 theorems here. So the first theorem deals with the construction of a von Neumann algebra. So take a 4-dimensional oriented smooth 4 manifold, and it turns out that making of its smooth structure only, nothing else, just smooth structure. A von Neumann algebra can be constructed from this data, which is geometric in the sense that it's actually generating operators are local operators. So something understandable from the viewpoint of the manifold itself. And especially as a 4-dimensional phenomenon, this operator algebra contains the appropriately bounded, complexified algebraic curvature tensors. So these are curvature tensors which either are real true curvature tensors coming from a metric, or just formally have the same symmetry. This is what we call algebraic curvature tensor. So among these elements of this operator algebra, the curvature tensors appear. This is a special 4-dimensional phenomenon. I will try to point out this point. And the Neumann algebra itself is not something very weird, but a type 2-1 hyperfinite factor. And we know that up to abstract isomorphisms, this algebra is unique. So it's interesting that it's from the plethora of four-dimensional smooth structure, somehow we can distillate, get one single object. Sorry?
Yeah, go ahead.
I have a question. You partially probably answered it, but still, let me ask it. So, what goes wrong if your dimension of your manifold is not equal to 4?
So basically, all things work in 4K dimensions. So in 8, 12, so on. But the curvature tensors are not included in the higher dimensional case. I will show you this. So the curvature tensors are missing. So this algebra is less geometric in that sense, I think. But most of construction works.
Okay, thank you.
Okay. The second theorem, how this operator algebra looks like. So we can do some inverse construction. It turns out that the manifold that we started from can be embedded by projections, can be re-injected into this operator algebra. And moreover, because this algebra is, as an abstract algebra, is unique, we can ask how two different manifolds embedding looks like in it. And it turns out that if we take two Neumann algebras, four Neumann algebras for two different manifolds, and we take an abstract isomorphism between them, then although this isomorphism is not canonical, the difference between different identifications just induces diffeomorphisms on the respecting M and N. So it means that this construction is functional in the sense that if we consider the category of connected, oriented, smooth four manifolds, with the morphism being the diffeomorphisms, then in this construction gives a functor to the unique hyperfinite two-type one Neumann algebra, whose morphisms are the inner star automorphisms.
Sorry, I don't understand. What does it mean to embed a manifold into von Neumann algebra? I'm pretty confused by it.
You will see. So I construct a set of projects parameterized by M. I will
one at one point of a manifold, zero elsewhere. It's a projection, which is
Actually, yes. So this is a physical embedding because elementary event in classical physics is a point of space-time, and we associate to it an elementary quantum event projection. But I will explain this. Moreover, now comes the point of the Einstein equations. So if we now understand this embedding better, then it turns out that actually pulling back the so-called the scalar product induced by this Neumann algebra by its trace, then we can pull this back and we obtain a Riemannian metric, which will be definitely Riemannian metric over the manifold. And now if we have a Riemannian metric and we have an orientation, because by starting demand was all manifold must be oriented, then
okay, can I ask a question? It's Ludwig Dabrowski. So what do you mean? I mean, M is compact, or I don't remember. It was compact in your case?
No, not yet.
Okay, didn't assume it.
That's not assumed yet. At
So
some point,
what does it mean, Riemannian curvature not bounded?
because you said if bounded, which means
Yes. So in the compact case, this means nothing. This condition means nothing. But in the non-compact case, we have to assume appropriate finiteness for the curvature tensor, boundedness of the curvature tensor to belong to this. Because this operator algebra contains bounded operators. So
so it works also for non-compact manifold. Your general theory. Okay, thanks.
Yes. But at some point, I will switch to compact manifold because of technical reasons. Anyway, so if we have an orientation, the metric, now on this manifold, then we can talk about the Hodge-star operator, which in this case, we have to take two forms, acting on two forms, so in the middle half-dimensional forms, and it satisfies the square is equal to 1, and it tells that it's a self-adjoint element. And we can use it to generate a star automorphism, inner automorphism of R, which renders this star operator, this Neumann algebra to a so-called Hodge dynamical system generated by this Hodge star. And the punchline of this talk will be that the manifold itself, by its projections, preserved pointwisely preserved by this dynamics, and also the curvature tensor of so the curvature tensor of this metric belongs to the fixed point set of this dynamics, if and only if the metric itself solves the Einstein equation. So it is, you know, from the PD viewpoint, characterizing or solving or saying something about the Einstein equation is extremely difficult because it's nonlinear PD. Meanwhile, here we come up with some very simple linear characterization of it. And of course, it will turn out that this is based on classical facts about the curvature tensor. So nothing deep happens. It is just a reformulation of some classical facts. Okay, so this will be the second thing about the Einstein equation. And I will mention some third theorem and will not move into this direction. The third observation is that now if we assume that M is more of a compact, so far we didn't use it. If M is compact, then this whole thing so far generates a non-faithful representation of this von Neumann algebra, a certain complex separable Hilbert space, such that the unitary equivalence class of this representation is invariant under orientation preserving diffeomorphisms of the original manifold. So we can take one of its simplest invariant of this representation, the Murray von Neumann coupling constant, or the dimension von Neumann dimension of this representation. And this number, this is real, positive real number, non-negative real number, it will turn out that this gives rise to a smooth invariant of this four manifold. And this invariant is some sort of gives a so-called good balance, because we know that very sensitive invariants are typically not computable, but computable invariants are typically not sensitive enough. So this is somewhere in the between. So it turns out that the spectrum, so the range of this invariant, can be expressed by the Jones subfactor indices, so which contains some strange discrete part and the continuous part, we know it. And also, it's possible to obtain a formula for this gamma invariant for the connected sum operation on manifolds. So if we take the connected sum of two compact oriented smooth four manifolds, then its invariant behaves like this.
I'm really having problems reading your slides, because when I read is an element of a set of Jones finite indices, moreover behaves like it's just
shorter sentences.
But it's not a sentence. I mean, it's
no, invariant behaves like.
Yeah, but then it has moreover, which is I'm really having problems parsing the meaning of.
So beyond this.
Yeah, and then but you mean like it's the next sentence, right?
Yeah.
But then you miss the subject. So okay, it's very hard to read.
Sorry, I have a question about this Murray von Neumann coupling constant. What does it mean?
I will briefly mention it. It's just the dimension of the representation of the Neumann algebra module.
Sorry.
In the case of two type 1 factors, I will talk about this later. In the case of two type factors, there is a continuous range of dimension for the Neumann algebra module over the Neumann algebra itself. And this number, this non-negative real number, which is the dimension of the representation over the algebra, this is the coupling constant.
Mm-hmm.
And we can, starting from a manifold, we can construct a representation, we can construct its coupling constant, and this is the statement about it, that at least its range is characterized by the Jones set of factor indices. Moreover, I think it's correct to say, moreover.
No, but you're missing the subject. Moreover, what? Moreover, it behaves like, or
Yes.
more precisely, it satisfies.
Yeah.
There's no subject and
Yes.
verb. It's not.
I'm not an English speaker, but I think once you use it here, then
No, it doesn't work like that.
Anyway, okay.
Sorry, one little question about this coupling constant. So it is defined as a trace, this type 2 trace of some projection.
Yes. Well, I will talk about this. So you have the standard representation, and if dimension is smaller than 1, so the standard representation, then you can just take a projection from the standard Neumann algebra module onto this subspace where the representation occurs. And the trace of this projection will be the coupling constant, right?
Okay.
Roughly speaking.
Thank you.
Okay.
Thank you.
May I have a stupid question? Why people use the gamma instead of one?
I use it. It's my notation. Okay, good question. Gamma, originally I wanted to use C because of coupling constant C, but the letter C is very occupied in topology because of the Chen character.
It's not
So this is gamma.
My question is about the behavior of gamma, 1 minus gamma. So 1 minus gamma is the inverse of the cosine square, first of all.
Yeah.
Second, it is strictly multiplicative with respect to this disjoint sum, this connected sum. So
This set goes under this operation. One can check.
I'm talking about the behavior of gamma.
Yeah.
So first of all, gamma is an inverse of x.
Yeah.
1 minus gamma is an inverse of x. And this 1 minus gamma is strictly multiplicative with respect to the connected sum.
So what we are saying is that instead of gamma, I would like to use 1 minus gamma as an invariant. It's not a question of notation.
Yeah. Okay. So you mean this X is more fundamental than gamma? Okay.
1 over x.
This side, but if you construct it, consider the whole thing, so this will be the dimension of the representation.
Okay.
So later we will see it. Why? Okay, I understand the question, but this is the natural notation because this will be the equal to the coupling. This will be the dimension of the representation constructed from M with standard Gelf and Neumann-Sigel construction. So basically everything is very standard. Okay, so now I would like to start to outline the proofs. So now let's check the first theorem. So the first theorem was about the construction of this von Neumann. How to do it? So it consists of two very simple steps. First is an observation that if we have any connected oriented smooth manifold, still not necessary to be 4, it can be even 4 times k. Then if we consider the PQ type tensors over this manifold, then it turns out that among these many tangent tensor bundles, there is only one which has an extra structure, namely contains a non-degenerate pairing, which is given by integration. So if we take the wedge product of the cotangent bundle with itself, then this bundle is this thing. Now I return to 4 dimensions. Okay. So if we take the two forms, then it turns out that integration eclipses this the space of compactly supported smooth sections with a pairing. Now we do a sort of bootstrapping method. So remember, I just want to use the smooth structure, nothing else.
So what is P?
P? PQ?
No, I understand Q. What is P?
This is just the tensor. P times the tensor product of the tangent bundle as Q times the tensor product of the cotangent. These are the PQ.
The P contravariant, Q.
Yes.
Covariant.
Yes.
Okay.
Can I ask again? So
Yeah,
you
go
say among all sub-bundles of TPQM, because T0 to M2 forms is a sub-bundle of.
Yes, sub-bundle.
So among all sub-bundles possible, the only one is this bundle of two forms, which has this.
Yeah.
Okay. Okay.
So just we don't use any metric or symplectic forms, any additional thing, just the smooth structures. Then this bundle is distinguished between all possible tangent bundles because it still contains a non-degenerate bilinear. Okay.
And sorry for this part, do you really need the dimension of M to be divisible by 4?
Yes, very good question. So even you can do it in even dimensions, but in even dimensions, this will be a symplectic form.
It will be
anti-symmetric. 4K plus 2 dimensions, it will be a symplectic form.
Ah, sure, of course, antisymmetric.
Yes.
Yeah.
But in 4K dimensions, it will be a symmetric.
Of course.
In all dimension doesn't work because you don't have middle dimension.
It is not a pairing, yeah.
Okay, so yes, so far everything works in 4D dimensions. I repeat again, the 4-dimensionality, we will focus on restrict to 4 dimensions only if we curvature tensors appear. Okay, but so far 4K dimensions, right? Okay, so we have this symmetric non-degenerate pairing, and how it is indefinite.
Can you come back a second to the previous slide? Sorry for.
Yes. You don't have Hodge operator there because you don't have metric. So this is indefinite because of that. Yeah.
Can you come back to the previous slide?
Can you come back to the previous slide?
Yeah.
I mean, this BRAC, alpha, beta, cat, L2M, what does it mean, L2M here?
Square summable, square integrable.
So this is 2 forms times 2 for the 4th form you can integrate. And you have orientation, so you can integrate. So what is the question?
I mean, what does it mean L2M? I mean, should be square integrable with respect to something or what? I mean, alpha, beta are square integrable with respect to some norm, or I mean, what does it mean L2M here?
Yeah, with compact support.
Compact support. So at least one should have compact support, but
Yeah. So you disintegrate it's a definition, right?
That's just a name for this left-hand side.
Yes.
Okay.
Yes.
A name.
You don't need to define L2 of M in order to define the scalar product, yes?
Okay, so L2 is maybe not correct notation. I just wanted to say that you integrate 2 things to get it, but it's not dependent on the metric or something. Maybe not correct to call it. We can put as an indefinite L2 scalar product, okay? But this is not important.
Just a decoration.
Yeah. I will not use this notation. But because we don't have any star operator or something there, Hodge operator is indefinite, but at least non-degenerate scalar product. But it means that it generates, at least gives rise to a quadratic form, which is an indefinite real quadratic form, which is meaningless. Okay, very important. This omega 2 Cm is an infinite dimensional vector space, right? So we have a quadratic form of an infinite dimensional vector space, and if it has signature, then it is something wrong because in infinite dimensions we don't have the concept of the signature. And this is now the point I would like to return to Penrose's point that now is a critical point to complexification. If we complexify this vector space, this space of 2 form, then we come up with and complexly extend this quadratic form, then we get a complexified infinite dimensional Clifford algebra associated to this pair. So if you have a vector space and a quadratic form on it, you always construct a Clifford algebra. And because this infinite dimensional Q is indefinite, it doesn't work in real over the real numbers, but the complexification kills signature. So we have a well-defined complexified Clifford algebra associated with this structure, and it is well known that it has this structure. So in infinite, maybe you use this picture. This is infinite tensor product of 2 by 2 matrices. This is the comes from the theory of classification of Clifford algebras over the complex numbers. So this is the so-called complex periodicity, which gives this classification.
But sorry, is it valid for infinite dimensional Clifford algebras as well?
Yes, this is my point. So you get an infinite dimensional complexified Clifford algebra.
Yeah, we know this, but the classification of both is also for finite dimensional Clifford algebra system.
Okay, we consider this as a sort of inductive limit of this.
Okay. Right-hand side is quite clear inductive limit. I mean, you have matrices of growing number, included one in the other, but what is the inductive structure of CM and the isomorphism?
CM, what is the...
You should have a family of finite dimensional
Yes, actually the family, this is, yes. So this is, for example, this for the tail, it is a family of increasing number of finite m by m matrices.
And it always exists for any infinite dimensional vector space?
Yes. Of course, you have to see this, but it is actually, just to cover myself, maybe shorten the discussion, I just now want to repeat some arguments from Alan Kohn books. I learned this from noncommutative geometry, that the first example for the type 2-1 hyperfinite factor is the infinite Clifford algebra. Okay, so I just want to...
In that sense, okay.
Okay, just to cover myself. But of course, you have to check things here well. Anyway, so just quickly, what happens here, this Clifford algebra is a complex star algebra whose star operation is by standard Hermitian conjugation of matrices. And also I call attention that this symbol will denote the Hodge operator. Meanwhile, this symbol will denote the adjoint in this algebra. Okay, this is the class of notation. And what we can do then, if we take an element in this Clifford algebra, then this inductive structure you mentioned says that it belongs to some smallest finite algebra, and we can take the normalized trace of this element divided by the size, and in this way we can get a trace on this Clifford algebra, which doesn't depend on n, easy to see. And we can define a linear inner product on this Clifford algebra by taking the usual product using the trace, which again you have to prove it is non-degenerate. And we come to the second step, which is just the formal completion. Then we can complete this algebraic object so far, this Clifford algebra. We can complete by the norm, which is induced by the scalar product, and this makes CM into a complex Hilbert space. And if we take its BH, and by BH the Banach algebra 1, the Dimroff, and then last integration on this algebra extends to the Hilbert space, and we just take the image of this left multiplication representation and take the double commutant or bicommutant of this, then we get a von Neumann algebra. And this is a standard fact that this is a 2 type 1 hyperfinite von Neumann algebra. So I did nothing special here. Just it was a bootstrapping, I repeat again, we started just from the smooth structure. We got a quadratic form and so on, and finally quadratic form got a Clifford algebra, and then did a completion of it, and this is a von Neumann algebra.
I have a question.
Yeah.
So your positive definite scalar product.
Which one?
Is defined by means of the trace.
Yes. Okay, this is standard fact.
But on differential forms, you have also the scalar product coming from the Hodge star. My question is, are these two positive definite scalar products related?
I was thinking about it. They might be related, but the relationship is not obvious. For example, this is independent of metric, but if we use this Hodge star, we have a metric, and this other definite scalar product depends on the metric. So not easy to compare them. Even the Hilbert spaces are different, because with respect to that L2 scalar product, we complete the space, the section space of 2 forms. This is different from this Hilbert space,
And when you say different, do you mean non-isomorphic?
Hilbert spaces are isomorphic abstractly, but by construction they are not the same.
Okay.
So this Hilbert space is the Hilbert space completion of this Clifford algebra. Meanwhile, that Hilbert space is the Hilbert space completion with respect to another scalar product of the space of sections. So these are not absolutely, not obviously the same things. So good question how to compare it.
May I have a comment?
Yes.
So I think that the construction of Clifford algebra, the natural setting is the vector space together with a quadratic form, and typically over the real numbers. But here, this Hilbert space, which is constructed afterwards, is only to yield finally a von Neumann algebra, which should be already represented. Von Neumann algebra should act on something. Okay, there is an abstract.
Yeah. This is actually just standard representation.
Yeah, I have regular representation, but I think. But if you for example, there is also C-star algebraic construction of Clifford algebra, and this is done in a universal manner, and then there is no Hilbert space at all. There is no scalar product, but still you should start with a quadratic form. So the quadratic form is given from the start. So vector space and quadratic form, and then you perform the construction of a Clifford algebra.
Yeah.
So this is my comment. Sorry.
Okay. But here, anyway, so I did this completion just to get this formula. This is why I use this completion. Actually, that's not that possible. Okay. And now let's just feel this is the von Neumann algebra. Continues to have a trivial center factor. It contains a trace, which can be expressed by the usual. This is the geometric meaning, so it is scalar product of the image of the operator in the Hilbert space with the unit. So, and the point is that starting from an arbitrary smooth M, 4-dimensional, we somehow came up in a natural functorial way with a unique von Neumann algebra. This is, I think, for me, it is remarkable. And let's see what can we get from this thing. Okay. So how the structure of this Neumann algebra looks? First of all, every vector space in the Clifford algebra, vector space canonically included into the Clifford algebra. And now, because of this infinite dimensional situation, it's also true that the Clifford algebra now not canonically embedded into the whole space of complex linear endomorphisms of the space of complexified two forms. And we can take the advantage of this embedding to say something about some elements of this Clifford algebra. This is the way how to compute the trace using this embedding. You just have to take, with respect to any metric, we just have to take the orthonormal basis. And if we have an element, at least in this linear endomorphisms, then we can compute the trace in this standard way. And it turns out that if trace exists, then this operator already will belong to this Neumann algebra.
Sorry, so this embedding is simply the Clifford multiplication.
This
Composition of these two is Clifford multiplication.
What do you mean by Clifford multiplication? Clifford multiplication is called yes. Actually, the Clifford module. Yes, you are right. Actually, here we use a Clifford module construction. Yes. I just and then now comes the 4 dimensions. In case of 4 dimensions, we are embedded in the two-dimensional tensors are embedded into this Neumann algebra. Why? So this denotes the algebra of bundle endomorphisms. So these are local endomorphisms, fiber-wise endomorphisms. And of course, you know that it contains in the full.
Can you use a pointer instead of your finger because people on Zoom don't see?
Okay. Could you see my?
No, of course they cannot.
Okay. So this space denotes the space of bundle endomorphisms. And this is the space of the previous complete abstract C-linear endomorphisms. So it is a subalgebra of it. And the observation is now that curvature tensors in 4 dimensions belong to this subalgebra. and how it looks like. This is now one of the key slides now of this talk. It is possible to prove that if we have a Riemannian metric and we can decompose using the orientation and Riemann metric, we can decompose the space of two folds into anti-Sergian parts. And in this decomposition, the curvature tensor will be 6 by 6 point wise, 6 by 6 matrix, and its irreducible components contain the scalar curvature, the positive value tensor, negative value tensor, and the traceless Ricci tensor. So you can see, and this is a special four-dimensional phenomenon, emphasized again, that the curvature tensor in 4 dimensions belongs to this endomorphism algebra. And if you look on the previous trace formula, for a pointwise defined operator, you can, using the pointwise trace, you can even work out a more understandable trace. And this will be just the total scalar curvature of the trace. The Neumann algebra trace will be just the total scalar curvature of the Riemannian tensor. And if this is finite, so of course the compact manifold is almost true. If this is finite, so finite scalar curvature case, total curvature case, the curvature tensor will belong to this Neumann algebra. Okay. And now I come to the embedding, what you asked, how to embed. Now we do converse construction. Take a point now, I will just repeat again, I will just repeat some standard machinery for algebraic geometry. How in algebraic geometry we embed the algebraic manifold into the space of its sections. How to do it? Just pick one point, and we can consider that subspace of two folds which vanish in that point. And we can take this subspace, and this is now the formula what I want to correct, because x's are missing from here. So
well, you can just use that.
So
or you can use this.
yeah, black one. Yeah.
Yeah, and maybe I have to. So
yeah, but you have to switch into an eraser to erase.
okay, maybe I repeat what I want to write here. So this is here just x is missing. So you have to take the Clifford algebra. Okay. So in total, I just want to say that this will be the local Clifford algebra generated by this two forms. And we can take its closure, what I denote by Vx in the Hilbert space, and the projection onto this closed subspace will be a projection which will belong, you have to prove it, it will belong to the von Neumann algebra, and in this way we obtain in appropriate sense continuous and so on injective embedding. Okay, so this is the embedding. So this is very physical, I repeat again. So this is a classical event of space-time, and this is an elementary event in quantum theory.
Okay, so sorry,
yes?
so correct me if I'm wrong. So this is just a continuous injective map and nothing more, yes?
Yes.
Okay, so because I'm not very much category theory minded, but still, when I see something like M a manifold embedded in a von Neumann algebra, I'm a little bit confused. But okay.
Actually, again, not so exceptional what I do. There are some papers when people embed Riemannian manifolds into Hilbert spaces by heat kernel techniques. So this all exists. So somehow you can embed finite dimensional manifolds, Riemannian manifolds into Hilbert spaces. So this exists. It can give you interesting results.
Okay.
Okay, and now what about how to compare to embed this? Maybe I very precisely have to finish at after 90 minutes, right? So I
mean, if you're by a couple of minutes.
If you don't understand something, then please stop me. So anyway, as I mentioned, if we are given two manifolds, M and N, we can consider the embedding into this abstractly isomorphic von Neumann algebra, and this embedding is not isomorphic. This isomorphism is not canonical. So there are many ways of identifying different von Neumann algebra, and it is easy to see that if you have one embedding, this is just from category theory. Another embedding is just obtained by doing sandwiching or by automorphism of the objects. So now we have to understand how the automorphisms of the von Neumann algebra look like from the viewpoint from the geometric viewpoint. And it turns out, I don't want to prove it at all here because no time, that if you have the extra information that you are given a manifold, then every star in an automorphism of this von Neumann algebra splits into the product of a gauge transformation. So bundle automorphism of two forms. I call it gauge transformation and orientation preserving diffeomorphism. So this is the decomposition. And this is also the decomposition on the n side, manifolds. And if you have a different isomorphism, just looks decomposed like this. So it says that the different identifications preserve the manifolds because we know that gauge transformation leaves manifold pointwise fixed. And diffeomorphisms move manifolds themselves. So if we switch to another identification, these still leave the corresponding m's and n's the same up to diffeomorphism. This is what I mentioned, that this is a functorial construction. So diffeomorphisms of the manifolds induce inner automorphisms of the von Neumann algebra.
So sorry, I to be sure, do you claim that every such isomorphism between von Neumann algebras like this is of this form?
Yes, it is just category theory. If you are in a category and you have two objects and you have an isomorphism between them, then any other isomorphism is obtained this way. Just do the automorphism of the objects on the both sides.
Sorry, sorry.
Adam?
Yes, I have a question, but I have interrupted you. You have not finished your sentence, so sorry.
Just wanted to say this. This fact comes from abstract category theory.
You are not happy, Thomas.
No, I'm not happy.
Why?
Well, I doubt it. Because you are associating with your manifold some fundamental algebra.
Yes.
Cooked up with sections of some bounds.
Yes.
Okay. But then you have some abstract fundamental algebra.
Yes.
And you are claiming that every automorphism of this von Neumann algebra is induced by a combination of gauge and
saying that if you are given one.
If you are given one. But but you cannot assume this.
Maybe no. I claim that if at least on a dense subset of the Clifford algebra, whose completion is this Neumann algebra, I can prove, but I didn't prove it here at all, that, and you have the extra data, you have a manifold, that every inner star automorphism decomposes in this way. Yes, I think interesting observation. But I don't explain it. Didn't explain it now.
So do you claim that such transformations are dense in automorphism of the von Neumann algebra? Inner automorphism of the von Neumann algebra.
Yes. If you are given the extra data, that manifold is embedded into it. I can prove it.
Okay.
Yes, and just one remark about outer automorphism. So because we have a representation of this Neumann algebra, we could also say something about outer automorphism. There is a theorem by some Japanese mathematician from the 70s. I don't know that in the strong star topology, the inner automorphisms are dense in the space of all water. So basically, you can approximate all automorphisms in this way. So yes, okay, interesting question, and not absolutely not straightforward, but we can discuss it. That at least on the dense subset of the Clifford algebra, we have such decomposition, and these transformations present the manifold pointwise. Meanwhile, diffeomorphism, of course, maps into itself, but not pointwisely. So the point is that if you move from one isomorphism to another one, it will not change the embeddings. And this is what I want to say, that some intuitive point, that in this sense, all smooth form manifolds are embedded into a common universal von Neumann algebra. And this is what I would like to call, as physicist, that is a non-commutative common generalization of all four-dimensional physical spaces. And I want to take some advantage of this viewpoint later.
Sorry, could you please go to the previous slide for a moment? I'm not so sure whether I understood the meaning of this adjoint, this add correctly.
Odd operation. Conjugation, yes. Sandwich.
Yes, but still, I don't know whether those lands in the correct spaces. So F acts between von Neumann algebra, which is a completion of this Clifford algebra, yes? And
Yes.
this is constructed with the help of these smooth forms, yes? And then what? You take this gauge transformation.
So if this alpha is an inner star automorphism of R, then I claim that on the dense weakly dense subset of the Clifford algebra, it decomposes by this, and you somehow extend this to the full R. But maybe automorphisms are enough to understand the dense subset.
And the star in this add 5 to -1 star is this one.
Yes, how to say, pressure of notation. So a diffeomorphism generates an action of space of two forms. And this is by Kuhlbeck.
Kuhlbeck.
Okay. So this is the action of a diffeomorphism by Kuhlbeck on the space of two forms. Because you remember, somehow these two forms are in the background of the school construction. And in this way, the action of the space of two forms induces an action of the endomorphism of that space, and then we get an action of the Clifford algebra, and we extend it to the Neumann algebra. This is how diffeomorphisms act on the Neumann algebra. Actually, they will be unitary elements.
But still, I think that there is one additional out from this automorphism, which is unnecessary. So probably if you have gamma, which belongs to C infinity of M to out of this bundle, then probably it shouldn't be add gamma, but just gamma itself. Am I right? Or?
No, maybe we are just now confused by notation. So I cannot use I can use
This is the meaning of the gauge transformation.
Yes, I write down what do I mean. So this is the right.
Yeah, but you didn't click it. Yes, now.
Okay. I just want to write this, that if you are given a two form, then you can opt in this way, that by gauge transformation, it's not exactly point, right? Something wrong. What happened?
I don't know.
What I'm seeing is only omega is mapped to gamma and nothing more. Is it right?
No. I cannot finish my formula because of technical reasons.
Okay.
Well, maybe.
Try to use your finger, maybe. No.
No, maybe.
This I don't understand.
Pen is locked.
Yeah, please look.
Wait a second. Okay, try again, because I can write with them.
Yes.
Try again. Sorry about this. No?
Somehow. I suppose it covered with some fingers.
No. It's a glitch. I don't understand. I mean, because I can write with a mouse, you see?
Yeah. I try to use my finger also doesn't.
No, somehow this will switch to. Now, this is really strange. Okay, let me do the following. Let me put it in.
This point later. Okay. So this gamma actions by pointwise action of two, and the phi defaults out by two.
Try to use a pointer again, or. Okay, now it works. And try to switch to the pen.
Yeah.
Mm-hmm. Okay, and now try again.
Now it works.
Yeah, I apologize about it. This was a glitch.
Oh.
Yeah, but this does not erase. Your finger doesn't erase.
Anyway, so can you understand this?
Yes, it's a pointwise.
The pointwise action of automation and moreover we have not pointwise action of additional just by pull back.
Yeah, and for this gamma, I'm fine with this gamma, but then you have add gamma, so.
Yes, but now we are on
now conjugate.
Two, yes. If you now move to and omega.
Okay. So.
And then this will be adjoint. Okay.
Okay, so everything takes place in this endomorphism. So
Yes.
the reason for add. Okay.
This is essentially already the Clifford algebra, and you just extend it to the Neumann algebra. So,
okay, that makes sense. Okay, thank you.
okay. And now there's the point again that I think this somehow intuitively gives you universal quantum space or quantum space-time which contains in a natural way all possible smooth four-dimensional structures. This will I use later for physics.
And sorry, just one quick question. You mentioned that this functoriality, but your morphism between your manifolds are what? Just smooth maps?
No, the categories consist only diffeomorphisms of manifolds, self-diffeomorphisms, not maps between them. There is such category contains the isomorphisms of the object only.
Diffeomorphism. So,
yes.
So you cannot take different smooth manifolds in some sense, yes?
Yes, but I don't use any map between them. I only use the self-diffeomorphisms in the previous construction. So this is the category of smooth four manifolds, and the morphisms are the diffeomorphisms of them.
Okay, so there is no morphism between different manifolds. One could say
that exists, but I didn't say anything about it. Of course, they can be somehow represented in this phonology, but I didn't think about it. But yes, certainly you can say something.
So okay, if you start with M and then you change the you have different manifold, but which is diffeomorphic. So in fact, not really different. Then you perform this construction. You get something which is functorial. But if you start with a quite different another n manifold, there is no relation between this construction of two unfactors, yes?
Yes. So I don't use any map between M and N in this construction. I just use the self maps.
Self maps.
M and N. So there is a category containing the. So these are just maps here and here. So this. But anyway, this means that this diffeomorphisms map into inner star automorphism of the corresponding Neumann algebra.
Okay.
Anyway, and now I come to the how to construct a metric. Again, I skip many technical points because of also time. You just simply take a point, two vectors on the tangent space, and you extend them to compactly supported vector field somehow, and you take the corresponding Lie derivatives, and it turns out that taking the commutator of the projection with the corresponding Lie derivatives remains in the von Neumann algebra, and you just something wrong again because
you chose a pen instead of a highlight.
Yes,
That's a highlighter, yes, but it's okay, don't worry.
okay, so in this way we remember if I can delete somehow this.
Yeah, the eraser is this white rubber. No, that's the highlight. That's the eraser. Yes. 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 Yes.
So these things here is just the scalar product on the Hilbert space. So A times B conjugate. So I just spoon back the basically the Hilbert space scalar product to the manifold.
Sorry.
In this way,
Map this Lie derivatives into this von Neumann algebra.
again, very good question, and is the same as I said before that. We have this vector field, from that we construct the Lie derivative. Lie derivative and the Lie derivative acts on two forms. Again, this is the critical background technical. So we have a linear action on two forms, and again, this induces an action on the endomorphism.
Your algebra is Clifford algebra.
Yes, but it was embedded into the endomorphisms of the two forms.
So your Clifford algebra R is what? Is this Clifford algebra or is this endomorphism thing?
It is embedded into the endomorphism thing. So I use that.
But R is different from endomorphisms.
Sorry?
R is a smaller, it's a subalgebra of endomorphisms.
Yes. Yes, okay.
Okay,
Yes.
so LX is an endomorphism.
Yes, so you asked this point.
One checks that.
Yes, I completely missed it. So you can see that actually they will belong to the von Neumann algebra. I can again return to this point later. You just have to compute the trace of these operators. And if it is finite, it will belong to this Neumann algebra. Okay, completely. I made one comment in the parentheses that at this point you have to check many things, but I didn't check it. But anyway, all things what you can see here can be mapped into Neumann algebra objects through the action on two forms, on the space of two forms.
Can I ask something? So, can you remind me in the embedding that you construct, did you use a Riemannian metric?
No,
No.
not at all. So now again, do you do some inverse mesh direction?
Okay, yeah. It's,
opposite direction. I pull back the scalar to get a Riemannian.
I couldn't remember.
And this is Riemannian metric to return to your point, because this is a definite scalar product, so we have no signature. But anyway, so these are good questions, and I skipped them. These are technical questions. And again, now having a Riemannian manifold, we can have the Hodge star, which is this symbol, and it will turn out, if of course it squares to 1, and it will be unitary, and taking adjoint with it will generate a one parameter inner automorphisms group of the von Neumann algebra, and we call it as the Hodge dynamical system generated by this whole machinery so far. So this T, abstract T here, of course it means time, but it has nothing to do with any time development on the manifold. So it is very abstract dynamical system time. And now comes the point, if I return for a moment to this slide, you remember that this is a standard construction of the curvature tensor in 4 dimensions on 2 forms. So this will be a 6 by 6 matrix, so 4 by 2 is 6. 6 by 6 matrix, and the Einstein equation says that the traceless Ricci tensor vanishes. This is the meaning of the Einstein equation. And it's very easy to see that, of course, in this basis, the Hodge star is just 1 minus 1, the matrix. I would like to write down, but again,
well, try it again. I mean, is it switched on? So try to switch it again into a highlighter and back into this. Try to go back to the highlighter.
What is the highlighter?
Well, that is what you point with. No, this is a hand.
Yeah.
Highlighter is this thing which allows you to highlight.
Yes.
Yes. Okay, try to highlight. Let's see if it works. Try to highlight. Oh,
Okay, doesn't do.
I'm really sorry about it. This is so I honestly don't understand why.
Yeah, the technology always
Works. Sorry, I completely, yeah, mouse works. I don't understand why the pen.
no, anyway, I try again.
Okay. It should work. I really don't understand why it doesn't.
Okay.
It seems to be random.
It's it. So in this basis, Sergio made the 2-form basis. The star operator simply is this matrix. And it's very easy to see that if this component, then it will commute with the curvature. And if not, this is a very simple statement done by Zinger and Thor in the 60s. So a very simple algebraic characterization of the Einstein condition is that the Hodge star commutes with its own curvature tensor.
But the consequence of the Einstein equation is that scalar curvature also not vanish.
No.
Because the dimensions
Einstein equation, I mean the
Rij,
yes,
minus 1/2 Ricci.
equal to lambda times g. This is what I mean by it.
So this you mean?
Yes.
This is what we from the Einstein equation.
This is what we call Einstein manifold geometry. If the Ricci curvature is proportional to the matrix. Okay, you are right. If lambda is 0, then the scalar curvature is also 0. But
no,
the cosmological constant is not 0.
No, the definition of the Einstein equation is that Ricci is equal to 1/2 scalar curvature times g.
Yes. Yes.
It's a completely different condition than you are writing here.
No, in differential geometry, a metric is called Einstein if satisfies this equation, which is just the vacuum Einstein equation with cosmological constant. So what I am saying now, and return to this part, what I am saying now, it is written here. So it is a simple fact. Basically, I solved it.
GÁBOR, you're right. I mean, according to TP, yeah, this is exactly.
Yes, but it's not Einstein in the sense of Einstein.
Einstein.
What people in Riemannian geometry call Einstein.
Yes.
Okay.
Okay, physicists say this is the Einstein equation with cosmological constant. Physicists also say it.
That's exactly what I found.
I think so. So this is the vacuum Einstein normal, but cosmological constant. Here, in this case, that equations you mentioned reduces to this form.
And
then which goes into this round.
And if lambda is equal to 0, you call it Ricci flat.
Yes.
Okay, so you mean Einstein with a cosmological constant?
Yes. So and now point again. So it is a okay. Because basically I proved it that if the curvature tensor commutes, with its own Hodge star on 2 forms, then it is if and only if this equation satisfied. And now we can see that we introduced very artificial layer dynamics generated by this Hodge operator, and now we can see that it will be belong to the fixed point of this Hodge dynamics. And again, just already one gets excited by this and even can characterize the Einstein equation in a very abstract operator algebraic sense, now completely forgetting about metrics and so on and PDs. We can say that let M be a manifold, like so far. Oh.
No, yes.
Let M be a manifold, so far, and consider its Neumann algebra. And actually, even this manifold is not an input now. We can say that the refinement of this Neumann algebra is a pair such that an operator which satisfies self-adjoint and its squares to 1, so mimics the behavior of the Hodge star. And we can say that this abstract operator from the Neumann algebra solve the whatever it means quantum vacuum Einstein equation with respect to this refinement if the following things are true for that. First of all, it must be self-adjoint because the curvature tensor is a self-adjoint object. It must satisfy this equation, which is the algebraic description of the Bianchi identity for the curvature tensor, and commutes with this star, which is just, we could see the characterization of the Einstein condition. And this is a linear equation, and very easy to solve it. So whatever it means, we have some quantum generalization of the Einstein equation, and again, just return to one sentence to Pedro's comments. Now, this is a completely complex thing and completely linear things, because very, very easy to solve this equation. You just take one operator and you just have to do projections to fulfill this condition. So basically, starting from operator projecting onto an appropriate subspace, you get a solution of this equation, but I don't know if it has some meaning.
Wait, are you trying to tell us that with the help of this Neumann algebra construction, you kind of linearized gravity?
Yes, but the key concept, the metric, is completely missing from this description. So if I try to move, and of course this is my hidden aim, to move toward quantization, of course I don't want to consider the metric as the fundamental object. I want to consider the curvature operators as the fundamental object of gravity theory. And in this, if you accept this, I could argue for it and against it. But anyway, if you accept this, then in this abstract curvature tensor as an operator framework, the Einstein equation can be linearized in a linear way.
Sorry, I'm a little bit confused by this Bianchi identity. This tau is just the trace, yes?
This is cyclic. I mean that cyclic property of the curvature tensor. So this is
but in this formula, tau is just a trace, yes?
Yes.
So this is like a codimension 1 condition, yes? So the trace is scalar. I mean a scalar valued. So this looks like a very weak condition on Q.
Yes.
So
this is why I don't know if it has meaning, this equation, or not.
So maybe it doesn't mean that it is algebraic Bianchi identity.
Anyway,
maybe it's a consequence of algebraic Bianchi identity.
No, what you can prove, if Q is a correct curvature tensor, comes from the metric, then and you compute this quantity for it, it will be just the classical algebraic Bianchi identity for that metric.
No, it cannot be before what Adam said.
Yes, it can.
Bianchi identity is pointwise, and this is the global condition.
Yes. If we talk about okay. So I don't want to say that this is a one-to-one characterization.
Okay. So some consequence,
and very general consequence, and this is why these things became very simple. So just linear and complex. Okay, the original Einstein equation is much more complicated. So just I want to say that in this framework, formally, you can very easily generalize the Einstein equation to something. So this is just a comment, it's just a remark. So I don't want to move in this direction more. Okay.
Sorry.
Yes.
Continuing objection or comment of Piotr, not a comment. So this is linear with respect to Q.
Yes.
As it is in the classical theory when Einstein equations are linear with respect to Q.
Okay, but not
But
metric.
you have induced this metric by this embedding. What is the relation between this Q and this metric? Is this curvature of this?
No, this is what I'm saying. This is now just an obstacle.
It's not related with the metric, which is induced by this embedding.
Yes, not related. Yes. So
What
this
is
is
how?
yes, good question. I don't know. I'm just repeating again that abstractly among the elements of this von Neumann algebra, you can characterize those ones which behave like the curvature term. But I don't want to say that they describe something. Maybe describe, but I don't know. And this is why they are very easy to solve. Maybe too big generalization. I agree. Okay, so this open topic, what does it mean? But at least I could, understanding the behavior of the classical curvature tensor, I can easily move this 3 points. Okay, now comes the how to prove that third theorem. But I will suppress it because also lacking of time. Maybe I completely miss it. Okay, and we can return to this later if somebody wants. So this is about maybe I just mentioned one thing. How to construct a representation from this whole machinery so far. Again, we just repeat the standard Gelfand-Naimark single construction. If we have a manifold which is embedded into this von Neumann algebra, then we have a set of projections, and we can simply introduce this functional, take the a times px, its trace, pull back to m, and integrate this function with respect to the metric what was induced. So everything is done in the bootstrap way. Everything here just provided by the original smooth stem. And this is a functional, you can analyze it, and then these elements generate a left ideal in this. And because of some reason, we take the completion of this ideal, of this Gelfand ideal in the Hilbert space, and because of some reason, we take its complement and just restrict the standard representation, so this multiplication from the left, we just restrict that multiplication to this subspace. It will be closed under this multiplication because it's ideal property. Anyway, so we get in this way a representation of this von Neumann algebra new one, which is not the standard representation. And it will turn out that, okay, I skip this. This is expressible, this invariant with the Jones indices. And now I would like to come to my last part and then try to finish quickly. Comparison of representations and physics. So, just general recalling that the hyperfinite two-type one factor has an extraordinary rich representation theory. Compared with the other factor Neumann algebras, this has the richest representation theory by the trace. And it is a theorem that all representations of the hyperfinite two-type one factor classified by their so-called Murray von Neumann coupling constants on R dimensions, which take values in the half real line. And again, just what coupling constant is, you just take the trace of the projection which projects onto that Hilbert subspace on which this representation is given. This is not fully correct because you can get higher dimensional representation than the standard representation. But now, forget it. I just focus on smaller dimensional representation. And it is possible to say that, of course, the Neumann algebra, this two-type algebra doesn't have irreducible representation. Every the representation decomposes, and, for example, given a representation by this x, according to this formula, it can decompose into integer part and fractional part. And of course, the integer part representation will be just copies of the standard representation. And meanwhile, the functional part, which belongs to the semi-interval, gives the interesting part. And now the question is how these fractional representations look like to understand completely the representation theory of the diagonal form. Okay, maybe just repeat it here again. So it's enough to understand the representations in this closed unit interval. And of course, the zero, just the trivial representation of the von Neumann algebra. The dimension given by 1 is just the standard representation by left multiplication, what we started with. And the standard representation has the following very interesting properties. 3 points. The first is that it can be constructed by the Gelfand-Neumann-Siegel construction from a Hilbert space, and the functional for this representation just is the trace on the von Neumann algebra. It is faithful, so you don't have to divide by any kernel or any ideal here. Second observation. The Tomita-Takesaki modular theory is applicable in a trivial way to this representation. It gives a modular operator, and it makes R into a dynamical system. However, this dynamics will be trivial because the tau is a trace functional in it. But anyway, we have then at least a trivial Tomita-Takesaki theory. And the third observation is that even this tau is a so-called Martin-Schwinger state for this representation. And also the Martin-Schwinger KMS state has a formal temperature, and you can compute this temperature for the standard representation. It will be infinite, again because of the tracial property of the Kubo-Martin KMS state, which is the trace. Okay, so this is the 3 standard points of the standard representation. What about these points for this geometric construction, what I outlined before? So what about this manifold induced representation with fractional dimension? And it turns out that you can repeat these things. So first of all, it was obtained by the GNS construction, and we use this functional for this construction. Remember, this is not just integration over the manifold. So this is something very natural. So this representation can be obtained in the standard Gelfand-Neumann-Siegel way. So this is the same. Moreover, this representation also induces a dynamics on the Neumann algebra corresponding to the modular dynamics, but this is not the modular dynamics, it's generated by the Hodge operator, and it satisfies its square is equal to 1. And this can be interpreted in a very interesting way, that this operator this function is invariant under the Hodge dynamics against some compatibility condition. So it will be made, the representation is preserved by this dynamics, and this state will give rise to a thermal equilibrium state. So something analogous to the KMS condition. But already the temperature of this thermal equilibrium state will be finite. And very interesting, maybe you never thought about this, that the Hodge operator squares to 1 can be interpreted as a temperature, because we know that in statistical mechanics, if you have a periodic dynamics, the period of that dynamics can be understood by statistical physicists as a temperature in that theory. So that discussing the differential geometric linear algebraic fact that it squares to 0, squares to 1, and these dynamics are non-linear, can be interpreted as the existence of a formal temperature in this set of representation, which in natural units will be just half of the Planck temperature. So this 2 is the same as this 2 here. So we completely mimic these 3 properties of the standard representation. Only difference is that this representation has infinite temperature, Meanwhile, this representation has finite temperature, and this is independent of the manifolds. Uniformly, this is the temperature. And this is now my cruising slides, final jumping into the unknown. So I have to interpret this whole story so far as the existence of a standard quantum field theory in the background. So the two type 1 factor somehow describes infinite degree of freedom quantum theory. There are some hints for that. And I just want to classify the representations of the two type 1 Neumann algebra as some phases in this quantum field theory in the background. So I introduce the following, challenging things. You can refute it if you don't like. So we have a unique representation of the four Neumann algebra given by the standard representation. I interpret this as a unique quantum phase of some quantum field theory, which describes a quantum space-time, whatever it means, a quantum space-time at infinite temperature, because the formal temperature of this representation was infinite by the ratio property of the trace, so the ratio property of it. And we can pass from the unique representation to an abundance of representations provided by smooth form structure. And these are just restriction to these three things in some sense. Instead of the Neumann algebra, we restrict ourselves to the fixed point algebra by the Hodge dynamics. So we replace this R this generates subalgebra, which is the fixed point subset of the Hodge dynamics. We replace the Hilbert space with another Hilbert space. Unfortunately, I skipped its construction, but it's Hilbert subspace of the original one. And we replace the standard representation with the restriction of it to this constructed subspace. And I want to see in this thing four-dimensional, particular four-dimensional vacuum Riemannian vacuum space-time, which has this formal temperature. So in my mind, finally, and this is my closing sentences, somehow in my mind, the emergence of classical space-time is a sort of phase transition by spontaneous symmetry breaking. So there is some infinite dimensional beginning, if you want to say, and by spontaneous symmetry breaking, because the temperature jumping, we select one particular space-time. So this is the spontaneous symmetry breaking. Actually, no reason to which one to select, but from a volume or abundance of representations, you choose one. And it happens at some finite, very high temperature, and this is how the space-time emerged.
Sorry, that's a very stupid question. I'm trying to understand how from this input data, so you have a von Neumann algebra, you have a Hilbert space, say it's a 2.1 at 1.5, okay? What, by the faithful representation? Yes. Okay. So how, from this data, a space-time emerges? I don't see a second. How does it emerge?
No, how to say? This is what physicists call a spontaneous symmetry.
Okay.
So somehow this structure has a huge symmetry group, automorphism group, everything.
Okay.
Somehow you break this automorphism group into some smaller group.
Okay, so
and how you select this. It's not explained here, but we replace what so spontaneous symmetry breaking is the symmetry breaking of some symmetry, right?
Yeah.
So here the symmetry group is the automorphism group, and if we switch this picture, then here the symmetry group is the diffeomorphism.
Wait, so
and this is a subgroup of.
So when you do the subgroup of some automorphism group of 2.1 factor, you say that this manifold then emerges?
Yes, I want to say, this is not a mathematically precise thing what I'm saying here. I want to say that, you know that classical explanation of spontaneous symmetry breaking. So this is a very symmetric space.
Yeah.
And you in one direction, you just this red arrow here, you just turn or break the symmetry somehow. You have infinitely possibilities. Any smooth four manifold in this moment works, and you just choose one.
Yeah.
If I say that if you somehow do this, you come up with this structure and want to implement this as a vacuum.
Okay.
So
I'm happy.
physical.
No, this is very fascinating. Yes, I'm happy.
Okay, so this is what I wanted to say, and I shouldn't exit directly. Yeah, just 45. Okay, so I'm ready for discussion. Thank you very much. And if I didn't answer some of your questions, we can contact through email or live, and we can continue this. And thank you very much again for listening.
Thank you very much for a very exciting talk. I mean, it was, yeah.
I hope.
No, this was very exciting.
Computer.
And you attracted some diverse audience, people who might rarely see came to your talk. So, Adam, fire at will.
Yes, I have at least two questions. One is about the
But for this talk, you must have 4 questions.
four dimensional. Okay. Yeah, but there are 2 forms, so I can also have 2 questions, like 2 forms. One is about local factors in quantum field theory. Do you see a way to somehow relate your theory to this von Neumann algebras, which, as far as I know, are of type 3.1, in fact?
Yes, this is some sort of discrepancy. I know that in algebraic quantum field theory, somehow the type 3 Neumann algebras are preferred. I never saw any mathematical proof for it. Is a sort of expectation in my understanding. But anyway, here definitely type 2 emerges. So I don't know why. But at least in just a historical remark, also von Neumann, favorite Neumann algebra was this one, this type 2 hyperfinite one, not just because of its uniqueness, but also because he wanted to use this. So anyway, so this Neumann algebra definitely has a statistical property. So it's well known because of the existence of a trace. So I have an absolute notion of probability here. This Neumann algebra has an interpretation of infinite degree of freedom. Physical, describing some infinite degree of freedom physical system. And from this viewpoint, I am satisfied with the emergence of this type 2 one thing, because gravity definitely might be the problem with the quantization of gravity is that you cannot reduce the number of degrees of freedom. So definitely something macroscopic thing, infinite, very field theory-like, and if you want to quantize it somehow, you should use on the quantum theory side an operator algebra which also describes some infinite degree of freedom. And the type 2 one thing is like that. Also, it was known to von Neumann.
Yes. But if I could comment on your answer, I believe that, okay, if you have type 3, it is also, it describes something which is of infinite degrees of freedom, infinitely many degrees of freedom. But probably the original von Neumann motivation was to interpret the probabilities in quantum theory in terms of frequency. But as far as he finally abandoned this idea from some other reasons. And this is related to the fact that the lattice of projections in this type 2.1, in fact, in any finite von Neumann algebra, finite in the sense of Murray von Neumann order, it is modular, which is more than being orthomodular. And this is related to this frequency interpretation of probability. And then from some reasons, he abandoned this idea. Okay, but I'm a little bit troubled by your...
Just to interrupt you, as far as I know, we didn't abandon it. He just had no time, unfortunately, to finish it. He complained in some letter that due to these governmental duties already after the Los Alamos project, he had no real time to return to his type 2.1 algebra and finish his quantum mechanical interpretation. This is what I know, it's a historical observation. So I think he didn't abandon it. just had no time, unfortunately, to work out.
Ah, that's interesting. Okay, and maybe one.
He did in his correspondences, so it was published by, I don't know, Springer. Contains all. This may be a letter to Berkhoff. He wrote this to Berkhoff in early 50s. He was already so busy, governmental, I don't know, advisor, and simply not complaining. You couldn't really few matters.
Okay, but coming back to this type 3, I'm a little bit worried since this type 2-1 hyperfinite factor is in some sense the smallest factor of them all. So
yes.
In some sense, if you want to extract these local factors which are of type 3-1, this cannot be a subfactors of your original 2-1 factor. And here you somehow argued that this type 2-1 encompasses all possible geometries, but local factors are related to some space-time regions, some parts.
Yes. But I think to answer this question is that the type 3 algebras appear if you try to quantize matter, whatever it means, matter fields. And here somehow the vacuum is very crucial. So the Einstein equation appeared in a vacuum form and no matter present here. So if I want to say this, I don't want to exaggerate this, but if it's sort of quantization of gravity, then it is just pure gravity. Somehow the matter, something different thing, and it might be related with type 3 Neumann algebras.
Oh, I see. That's interesting.
Okay. I don't know, of course, this is true or not. It's just challenging questions.
Yeah. Can we ask also?
Go ahead.
Okay, so again, I have maybe a naive question, or I don't know, maybe stupid, but you have representation of a Clifford or infinite dimensional Clifford algebra on this Hilbert space. You have its completion, okay, by commutant. And this Clifford algebra is, of course, a sub-algebra of endomorphism of omega 2 of your two complex forms. But in many places, you also treat endomorphism as elements of this von Neumann algebra. I don't understand which sense. Is it obvious somehow?
Yes. So of course the full von Neumann algebra doesn't embed into this endomorphism algebra. It has a non-empty intersection with this.
Yeah, but how endomorphism is represented on this Hilbert space? How endomorphism of the Clifford of the two forms and also probably, I mean, it should be isometry if it has to be automorphism of the Clifford algebra. How it's represented on this Hilbert space, I don't see. How it's an operator, how you associate an operator on H to endomorphism of omega 2.
Yes, so this is a very technical question, and I think I completely missed it. So actually you have to introduce many things.
There is a way. So your answer is that there is a way to do this. Okay.
Yes. Of course, of course, I did say, and it is not true, that the whole von Neumann algebra is embedded into this endomorphisms. It's not true. It is just that they have a
No, but my question is simpler, very stupid. How endomorphism is represented on this Hilbert space itself? Is it an operator for endomorphism of omega 2? You can associate operator.
In what sense you make this intersection? Like
in particular, but not only this, but also later, several times you use the fact that endomorphisms are elements of R of this.
I may write it down. So this omega 2 C complexified. These are not close the subspace of this Hilbert by its construct.
Okay.
It's true. And if I am talking about an endomorphism, then
okay, that's clear. That's okay because you build Clifford algebra as
not completely obvious that if you are given a component here and has appropriate finite trace and so on, you can extend the action from this subspace.
Oh, I see. So in that sense, okay. So induce from the action, induce action on it. Okay.
Can you understand this inclusion?
Okay.
Just by the construction of this interface.
Okay, thanks.
There is an intermediate, There's an intermediate stage here. So this is just
so this is just in the Clifford algebra. Okay.
And this is the complete to Hilbert's.
Okay. Thanks.
Great. Anybody else from Zoom?
I have one more question.
Go ahead.
So, am I right in saying that? Okay, could you go back to the slide where this Riemannian metric was constructed in terms of these Lie derivatives?
Yes. Again, I didn't say many things there.
So, oh yeah, exactly. So to this point, you have only assumed that M is smooth and nothing more, yes?
Yes.
So you didn't have any metric from a start, and then somehow you canonically, but okay, this construction uses this embedding. So I'm wondering, I didn't probably didn't understand it correctly. How much choices do you make up to this construction?
So sorry, repeat again.
How many choices do you make up to this construction? You have to choose what? You have a smooth structure, you have this.
I think you have no option. This is my point. At least I hope. So you just have this embedding. Okay, the question is if you can have other embeddings. I don't know. But maybe this is the simplest embedding. And after that you have it. You already just use the trace on which is unique on the Neumann algebra. So I want to say that this metric is canonical on the Riemannian manifold. It is just the pullback of the canonical Hilbert space metric on the Hilbert space.
Yeah, but
this construction was motivated by some such heat kernel construction. So also using heat kernels over a Riemannian manifold, you can pull back this. And I mentioned that using heat kernel techniques, Riemannian manifolds can be embedded into Hilbert spaces. And also this embedding can be used to pull back the scalar on the Hilbert space to the manifold, and you can compare the original metric with the pullback one. And from this comparison, you can get many interesting geometric results. So this technique makes some sense. And what I want to say again, that upon accepting that this embedding is unique or the best, simplest, I don't know, canonical, then this pullback metric is already unique.
Okay, so but somehow I'm confused and surprised maybe that this matrix pops out from nowhere. Yes.
Nowhere. So the Hilbert space has a metric. We don't call it as a metric, but in the scalar product on the Hilbert space is a Riemannian metric.
Okay, but on this Hilbert space, your scalar product was defined in terms of integration of forms. So this is completely canonical.
No. So this scalar product was defined in a canonical way. Just I repeat the general theory here. So this is the.
Okay.
This is the. So this is the way how we define in the standard construction of the type 2-1 factor, how we define the scalar product on the Hilbert space using the trace, the unit trace. So this has nothing to do with the Riemannian metric or finite dimensional Riemannian metric or something.
Okay, so the only choice which you are making is the choice of this embedding of M into this.
Exactly.
Neumann 2-1 factor. Okay, so this is very nice. Thank you.
Thank you.
All right. Anybody else from Zoom?
There's one more question.
Okay, wait. I want to finish Zoom first. No? No, go here from Zoom now. Let's take the room.
Yeah, I have a question. Yeah, it was also about that embedding. So you pull back a metric. Then the question is, with that metric now, M, Does it embed isometrically?
Sorry?
Does it embed isometrically?
Good question. I think if you pull back a metric from a space, it will be always isometric.
Yeah, exactly. So that was the first easier question, because it looks like, so for manifolds, you need large enough, let's say, Euclidean space to do that. Okay, but now if you use heat kernel techniques, you embed. I know, because you're saying you need probably with the heat kernel techniques, at least the ones that I can think of, all dimensions, like infinite dimensions, because you take the eigenvalues and eigenfunctions, and you need, to be isometric. So since you don't start with a metric and you get a metric and you pull it back, and by definition it's going to be isometric, looks like this 2-1 factor is large enough so that
exactly.
embed isometrically inside.
It is what I want to say by this remark.
Yeah, so like the existence of a Riemannian. Okay.
So this is somehow a common.
Yeah, but the fact that it embeds isometrically comes here from the existence of Riemannian, like from having a.
So the trace you have a
Yes.
Of course, the four-Neumann algebra is not a Hilbert space itself. You have to complete it, but you have at least a scalar product-like object on the Neumann, which is the trace.
So maybe to rephrase what I was saying, like if you had some other von Neumann algebra or something, some other structure, algebraic structure, you might not be able to embed it isometrically.
Good question. So, but at least the existence of the trace is very heavily used, and this is the property of the type 2-1 finite trace. So type 2-1 you need.
The second question is, so you have this embedding, assume now that you have dynamics on M, an action, a group action, and you implement it in some sort of cross product.
Okay.
It has to do with how canonical the embedding is, I guess, but it looks like it could be possible.
Very possible, and I completely skipped such things. If you have one more second. Yes, I mentioned here about the analogous properties of this fractional representation, and I was talking about how this state behaves, which was used to construct this geometric representations. So here, this F functional, I have reason or right to call this a thermal equilibrium state. The equilibrium state means that it is stable against the dynamics, right? So, and you can prove it that actually this functional is stable against the Hodge dynamics, and moreover, it is even stable against small perturbations of the dynamics. And this is what I want to tell to you, that if we have, in some appropriate sense, we can talk about the perturbation of this dynamics on the Neumann algebra, and again we can use this mysterious, if you like, point. I mentioned that any automorphism can be factorized into an automorphism of the bundle automorphism and a diffeomorphism. So it turns out that using this factorization, anyway, you using this factorization, every dynamics, which perturbation of this Hodge dynamics will be a dynamics also on the manifold. So we can regard the finite dimensional dynamics in some sense perturbation of this abstract.
So this says like there is some reasonable chance that you can consider more other like actions.
Yes. If you are given action on the manifold, using this factorization, you can lift it to the Neumann algebras. because all diffeomorphisms, this is definitely true, determining what kind of operators belong to this Neumann algebra. It is definitely true that all diffeomorphisms belong to the Clifford algebra, Neumann algebra. Maybe unitary elements there.
Maybe also if you consider something more, like something to see more of to restrict the choices for the embedding, to make it more canonical. Maybe you could ask something like to have the conformal diffeomorphisms acting on M, and ask that this action to be transferred in the von Neumann algebra through the embedding.
Yes, it's possible, but for something you need already a metric on M.
Yes.
Basically, I try to keep separate from metrics. I want to use metrics only if I need.
Yes.
But otherwise, for the constructions, I try not to use the metric. Yes. Or I have to use one. I want to use this canonical one, which comes from the pullback. So, just general comment. I expect this full construction is very rigid. You have no freedoms in it, and somehow because of it is natural. But the question is if it is good for something or not in physics. And also, I completely suppress that part, the smooth manifold invariant things. If this gamma invariant, what I denoted by gamma, that invariant, if it is really interesting for manifold theory or not. So this could be the point of exotic smoothness.
Happy?
Yes, thank you.
Anybody else from the room? Yeah, you go ahead.
This representation of manifold in factors, von Neumann factor 2, 1 is not canonical, yes?
Canonical, but what does it mean, canonical? So
I mean, given two non-diffeomorphic manifolds, you cannot say precisely what corresponds to this non-diffeomorphism on the von Neumann side. Yes, is that?
Yeah. So I don't have interpretation of the maps between manifolds in the Neumann algebra. Yes.
You don't have canonical.
The diffeomorphisms.
Yes. So you keep just one manifold and diffeomorphism on this, and you don't say anything about non-diffeomorphic manifolds. And representing that story in the von Neumann.
Yes, but what I wanted to explain that if you embed two different, not diffeomorphic manifolds into it, then and they have two separate von Neumann algebras. But if you compare these von Neumann algebras, is all possible way to compare these von Neumann algebras leave the embedding intact. So they just induce diffeomorphism of the corresponding two manifolds. So this is why I think I have right to say that there is a unique R for Neumann algebra, and it contains a sort of orbits.
Yeah.
All four manifolds.
But the impression is that probably when you refer to some other factors, you can get more canonical representation.
Yes.
For example, Zierelson problem in quantum mechanics, which is equivalent to some Kohn problem about 2-1 embedding of. Yeah, so probably it is just a very rough intuition. So maybe going into this direction, you can find something very fundamental for quantum mechanics from that point of view. It is also connected with smooth manifolds.
Mm-hmm.
And another this kind of imagination abstract stories is using Kalkin, automorphism of Kalkin algebra.
Yes, I wrote it in your.
I have impression that you can also make something profitable in that approach.
Yes, actually, I learned something very interesting. So the authors in the Kalkin algebra are very huge and
it's very non-trivial from set theory point of view.
From set theory point of view, yes.
So impression is that expectation is that probably you can distinguish some exotic structures.
Okay, but I do hope that even within this simple one, hyperfinite one, I can do some distinguishing.
Yes. But for example, if exotic force pairs exist, can you distinguish something?
Yes, it would be very good to say something about this one. I don't want to completely exhaust you, but even just exactly 168 hours ago, so last Wednesday, I gave a lecture in Igor's seminar, and in that lecture, I was talking about this smooth invariant sign, and I mentioned one observation that actually the injectivity of this gamma ion at 0. So yes. So remember, this gamma invariant is a map from the category of smooth four manifold into this interval, and we can ask about its injectivity at 0. So it was possible to compute this invariant on the standard force field. It is a simple observation that for the force field, the standard force field is this invariant is just 0, not surprising. And now we can raise the question: what about the injectivity of this invariant at the 0? Certainly, the exotic force fields belong to the image of the 0, and it is possible to prove. And I think it's interesting that the invertibility of the injectivity of this gamma invariant at 0 is equivalent to the smooth Poincare conjecture. So it is equivalent. Of course, I don't say it hurts to prove it, and also I don't want to say I proved it or something. Just not so difficult observation that the injectivity of this invariant at 0 is equivalent to the smooth Poincare conjecture. So it might contain some information.
So it excludes exotic spheres.
That excludes. So if not injective,
Equivalent.
if injective, then no exotic. But of course, I think that proving injectivity is as difficult as the smooth Poincare conjecture. So maybe it doesn't. Anyway, if you are interested, you can watch that my last week lecture from that Igor Nikolaev's Noncommutative geometry archive. That I include this observation.
Thank you. Okay. So you could start from arbitrary tensor. I don't know why you call it curvature. You could start from arbitrary tensors with not even two forms. And if you have some endomorphic of this, you can do everything what you did.
But how? So the starting point is missing that you don't have pair. You cannot construct Clifford.
Yeah, you can choose many such tensors satisfying your assumptions.
Really? Then you have to
really. For instance, take two forms with values in some natural vector bundles, and then you can construct something.
So you need some scalar product on the target one. So if you have vector bundle value, you have a twisted two form, then you can pair it only if you have some scalar product in the target vector bundle.
Okay, you can have even two forms, but then take the tensor satisfying all algebraic properties of the curvature tensor.
Yes.
Okay, arbitrary, not even coming from S as a curvature, and then you can repeat everything. So this is disturbing for me because
I have to understand what you have.
So you think you can have a tensor,
Yes,
which satisfies all algebraic properties, pointwise algebraic properties of the curvature tensor. Okay?
You will full Riemannian tensor or reach your one.
But acting on yeah, Okay, so this is a symmetric
Pairing, so in the very beginning.
no, not pairing. This tensor is defines an endomorphism on two forms.
Yes.
Not coming from curvature.
Yeah.
There are plenty of
Such tensors in this.
yes.
But they are included.
Yeah.
They are included.
Then you can do everything you did.
What do you mean? I did. So
You can construct this different algebra.
But this is the one I don't understand how, because you don't have the quadratic form. We don't understand it.
What is the curvature tensor?
Yes.
It satisfies some algebraic properties.
Yeah.
Bianchi, symmetry in pairs of two symmetric indices. That's all. Okay? And this tensor acts on two forms. As curvature acted in your.
Yes.
But this tensor doesn't come as curvature.
Yeah. It's called as algebraic curvature tensor. Yes.
Whatever.
Yes.
Okay? You can do everything you did. But you insist to call this algebraic.
I don't know exactly why, because we needed some selection rule.
What?
To rule out those tensors which cannot belong to this hyperfinite factor. And for this,
I'm not talking about the level of this completion. I'm talking about tensors.
yes,
Smooth sections of tensor bundles satisfying algebraic properties of the curvature tensor.
okay. So you come up with some algebra, but it's
Curvature is on the one tensor coming from the metric, but you want to forget about the metric.
okay. I did it actually. Yes.
Okay. Then you are doing something algebraic, you are completing then.
But how to complete? This is my point. How do you complete it?
Because you start.
So having the trace here, we use the trace to complete. So I think we can construct some algebraic.
How the trace can come from the fact that this tensor comes as a curvature tensor?
Here, the trace didn't come from that far.
Yes, exactly. It's independent.
Yes.
So you can do whatever you wish with this tensor, not being even a curvature tensor.
Yes, I know it.
Yes, and you can end up with these linear equations. You call
okay.
Yeah.
Yes.
So since any tensor can be used in your construction. So why do
you mean this? Yeah. Yes.
And what do you mean by Q solves the quantum vacuum Einstein equation?
Okay, maybe this is the next direction. So maybe this is just the next.
Okay.
So I just not exaggeration fully because in this operator algebraic framework and language, we repeated the properties of the Einstein equation.
Okay.
So maybe too broad repetition. So I made it before too many things to come into the game. It's possible, but come into the play. It's possible, but at least it's definitely true that these three conditions is a formally, these are not formally, very precisely satisfied by the real curvature tensors. And now I'm just saying that let's forget about metric, take any kind of tensor which satisfies this, and I call it as a vacuum, quantum vacuum curvature tensor. But okay, maybe you are exaggerating. So maybe you would need some more conditions here to get some interesting theory possible.
Of course, there is an interesting question. You can embed your manifold into projections in the phenomenal algebra.
Yes.
Okay, then they depend on a point. You can take derivatives with respect to this point. Okay, so this is not like an action in of this L as a homomorphism of endomorphism of this Hilbert space or whatever. It is a differentiation of this projection in some abstract algebra with respect to this point.
Yes.
It's a derivative. It's a,
Commutator.
no, it's not a commutator. It's a derivation with respect to this argument, this index of your projection. This projection depends on your point.
Yes.
So this is a function, projection valued function of a point of a manifold.
Yes. Yes.
And then you are differentiating this function.
Yes. Yes. Yes.
So this is not a commutator of these operators. It's a directional derivative with respect to the vector field of function taking values in projections.
Yes. Yes. I agree, but it's just a reformulation of.
No, it's not a reformulation. It's a
In non-commutative geometry, the differentiation is always
no
commutator. Doing
no. No,
in that con framework.
yes, but I agree. He's like a commutator with a Dirac operator.
Yeah,
But of what? Of a function. Now, this projection valued function, okay, is not of this form.
Which is comes formula.
It's a different type of a function. It's an indicator of for 1 point z. If you take if you would like to regard this as a function and wanted to commute with Dirac, you will obtain 0. Because this is 0. The value is 0 and 1 point. Okay,
but you said that this is a function.
No, Thomas, it cannot be like that. You cannot have an indicator function of 1 point. Then it would be uncountable.
So what is this projection?
Mutually
orthogonal projection. It's a function on the manifold. Projector valued function on the manifold.
Yes, it is indicator function of a point.
No, Thomas, no.
What is this?
You see, Thomas, sorry. Imagine that you have a family of indicator functions of 1 point. Then for different x's, you would have mutually orthogonal projections, and there will be uncountably many of them. But this is impossible in separable Hilbert.
Yeah. So you are raising more and more problems with this.
Another reason.
I didn't say these are orthogonal, mutually orthogonal.
Okay, so what is this px? If not you are writing x maps to px, so it's a function. Argument is x, and the projection is the value.
Yes. Projector valued function.
Yes.
But to every point.
So this is not a function in the sense of the commuting a smooth function with a Dirac operator like in Kohn approach. It's a function whose argument is a point, and you are and this isometric embedding comes from taking the differential with respect to this argument x.
Yes.
So what is px?
Saying that this is more like
Not an operator of multiplication by function.
So what is px?
Projection. Yeah.
Onto this vector. So you have to just start. You have to just construct the local topic constant because this local three-fold algebras depends on x. These are sub-three-fold algebras varying at least continuously with x, and you take just the projection onto the completion of this local three-fold algebras in their common universal space. So this you get a set of projection, family of projections.
Yes.
Yes.
So it's not an element of the algebra of smooth functions.
No, it's true.
So this analogy is phony.
Okay, but what kind of analogy?
Okay. Let's assume that we have defined this metric coming from this embedding. Okay. What was the connection? What was the relation between this metric, induced metric, and this tensor? You agree that this tensor could be arbitrary. Now, to be a curvature tensor of this metric.
But you can compute it. So once you get the metric, you can compute its curvature. And, you know,
Yes, but if you start this from arbitrary, you can do all this.
So maybe we have that some very simple point. You are talking about again about this equation.
For every tensor of type, of algebraic type of a curvature, you can do the same.
Yes.
And then you can reduce this metric by its embedding.
But this equation has nothing to do with the metric.
And this, what we call curvature, are not related.
Yes, not related. Yes, I want to see. Yes. I just want to characterize some sort of elements of this abstract form algebraic. And I don't. This is just some very formal generalization of the classical vacuum-Einstein equation.
And at the end of the day, these equations do not mean quantum vacuum Einstein equation for the metric induced by
Yes. No, they are yes, absolutely. Yeah,
so they are completely
absolutely not. Yes, this has nothing to do with the metric.
unrelated.
This is why I introduced formally this the so-called refinement. So you just take in the abstract Neumann algebra some abstract element which has the properties of the Hodge operator. It doesn't have to come from any metric. No, this is an abstract refinement of the Neumann algebra. You improve it with a pair, with its element satisfying this property, and in this defined structure, you can talk about those operators which satisfy this equation. So here, no metric absolutely used, nothing to do with the original metric. Yes, this is something completely general. This is completely operator algebraic.
My point was not that
but it's getting out of
my point was that they are unrelated.
But let's stop it because it's getting out of hand.
Excuse me, a very short question according to the questions of Thomas.
Go ahead.
Yes. Did I understand well that Thomas means that there is no any metric aspects in the part 2 and operator solve the quantum vacuum Einstein equation? In fact, I had the same question because the classical Einstein manifold is a manifold for which the Ricci tensor is a constant multiplication of the metric, and I had the intention to ask that which part of the second part, which part of this three part correspond to the classical concept of the Einstein manifold, because the classical Einstein manifold is a Ricci tensor is a constant multiplication. So should I understand that the non-commutative setting of Einstein manifold is that it forget the metric? I mean that which part of this three part Q star equal to Q, tau Q star equal to 0, and the last one Einstein condition correspond to the equality of the curvature tensor, the Ricci tensor equal to the constant multiple of the metric.
I think in this concept already no meaning to talk about Ricci tensor and scalar curvature and so on, because that is given only with respect to a metric decomposition. You need an orthogonal group to get this decomposition. Here, this Q already has nothing to do with any metric and scalar curvature and Ricci tensor and so on. Okay, I didn't explain it well how these equations come up, but if you understand these properties of the real curvature tensors, then you can write them in this language, in this phase. Now I am saying that now let's forget about kind of differential geometry, metric, curvature tensor, and so on, and just let's consider those operators in this abstract phenomenon which satisfy this equation. And this is why this is what I call as a quantum vacuum Einstein equation, but maybe it has no real benefit to say. So I don't want to say that now I came up with something very fundamental. This is just a formal, maybe too general generalization of the Einstein condition. So we have no metric here. We just have this extra structure, which originally came from a metric, so we motivated by the metric, but now we forget. Just take a set of element which squares to 1, and already you can write down these kind of equations, and even you know manifold you need here, or just not from von Neumann algebra and such a fit, and you can talk about such operators. So this is maybe too general and no useful naming. I agree.
Not too general. There are too many loose ends, which are unrelated.
I don't think so. So even this page can be a self-contained page.
Yeah.
You can completely forget what I was talking about so far. You can just consider this slide without anything.
Okay, if you,
I think it's meaningful page without any other additional information.
but
Motivated slide, but self-contained.
But it is okay. If this is definition, you can write what you wish.
Yeah.
But if you are writing that this solves the quantum vacuum Einstein equation, you are claiming something. And with this, I have a little problem.
Yeah.
Okay, maybe I shouldn't say so. So
Yeah.
Okay, but this now I'm just writing it. So I want to call this as the quantum vacuum Einstein equation, what is mean, and if an operator satisfies this equation, then I say that it is solved the quantum vacuum Einstein equation. This is just nothing.
It's a
But anyway,
it's a definition.
Definition. Maybe not useful for anything. It's possible. I didn't check it. But definitely by a real curvature tensor, these equations are solved. Definitely true. And now let's forget about everything. Manifolds, metrics, because operators, we can forget about everything and just take this formal definition in a Neumann algebra. And you have this thing. Maybe I agree with you, maybe this is too general, so maybe not useful for anything. Too many things follow, because this is just a linear equation. You take any operator, just project onto this subspace, and you already solve this equation. So,
But do you have an idea of what the space of solutions is? Imagine.
What is that computation? When you have this delta operator, what is the name of it?
Laplace.
Laplace, yeah.
Not Laplace. Oh, sorry, I'm already too tired. Something very BRST quantization. So in the BRST quantization, we move from a too big Hilbert space to some meaningful Hilbert space, Hilbert subspace. And actually, these three equations just project you from some too big operator algebra to a sub-algebra of it, which I say they are the Einstein equations.
So that's interesting.
Yeah, this is what I want to say.
Okay, let's really wind it up. Adam, if you could
Sorry,
make
I have just a quick question about this orthogonal projection. Could you characterize when Px is orthogonal to Py for different x and y?
I cannot, but they are not orthogonal. But they have common trace. The trace is the same because they are generated by unitary transformation. So they have the same trace, and I think they are typically not orthogonal. But if they belong to a different smooth manifold, then they will be orthogonal. So somehow orthogonality up to distinguish different manifolds. But if we have the same manifold, I think they are not orthogonal.
Sorry,
Yes.
but what do you mean belong to different manifolds? You work with one manifold?
I told you that this all four manifolds can be embedded into
this 2.1 factor?
Yes. Where is it? Here. So all four manifolds can be embedded into an abstract R. And if we now take one abstract R and consider the projections corresponding to M and N, I think they will be orthogonal.
Okay, this is your suspicion. It is
suspicion, yes.
Okay.
So somehow, even we can reformulate what does it mean being not diffeomorphic. It might be reformulated, but I don't know, as being orthogonal, the projection being orthogonal.
Interesting.
And of course, again, intuitively speaking, you have enough space because we are in infinite dimension.
Yeah.
So it's very possible that these manifolds under this embedding have enough space to be orthogonal to each other for every smooth structure.
Sorry, I'm not so sure. Correct me if I'm wrong. There are only countably many diffeomorphism types of four manifolds. Yes, is it right? Or
maybe you are right. Then this is not what I'm saying. Maybe this is algebra is still small enough to distinguish continually many different smooth structures. You are right. Maybe this is not true what I'm saying, but sometimes they are orthogonal. You know what I mean?
Okay, it cannot be. If I don't know whether the situation changes somehow if you assume that your manifold is compact, but in general you have continuously many different smooth structures.
Yes, maybe for compact manifolds.
And then you cannot expect that those will be orthogonal.
I understand. So maybe you are right. We have to assume compactness. In this case, it might be true because, as well as I know, you can prove that the compact four manifold can accommodate only countably many different smooth structures. And in this case, they are quite few, maybe. And they can already embed it orthogonally into this topology. It's possible, but you are completely right. In case of not compact four manifolds, they can have continually many different smooth structures, and they are the too many.
This is very tempting somehow to see geometric properties of your underlying manifolds on the level of those projections. I don't know. It sounds...
Sorry, repeat again. What?
I'm saying that, at least for me, it sounds very interesting to try to investigate some geometric properties of the underlying manifolds in terms of these projections.
Yeah.
This is easy. This is easy. For instance, if you have two projections, you can compute the distance between them. And since it's an isometric embedding, so this is the distance between points.
No. Thomas, I think that the distance between, you mean the norm of the difference? The norm of the difference of difference projections is always 2, as far as I'm not mistaken.
Even very nearby projects are always different.
For instance, if you have projections of codimension 1 in some, or dimension 1, okay, they form a projective space. And then on the projective space, you have a distinguished metric, which is a Fubini-Studi metric.
Yeah, but this is not the same as the metric coming from the norm of this.
Yes. Therefore, I say no to your computation. It's this natural distance between subspaces, which are images of this. Yeah, this is like in a Grossmania. Okay, this is in isometric embedding. So this is okay.
Okay, let me ask the final question. It's a very simple one. Could you tell me, please, what is the K-theory of this 2.1 factor?
It has the only factor which has non-trivial K-theory. So the K0 is R.
Okay, that is what I'm saying.
All other factors have 0. Yeah. And because basically we could say because it has too many representations. So K0 is R, the K1 is 0.
Okay, that's what I expected. But thank you for
just 1 minute comment and question. 1 minute.
Make it fast, please.
Yes. The subject of your talk is that you embed an Einstein manifold on the space of projections of a very big one-Newman algebra. But actually, when we get a compact manifold, for example, the easiest examples of an Einstein manifold of dimension 4 is CP2, and CP2 is embedded CP2 is embedded in M3 of C in the space of a 3 by 3 matrix of complex dimension of complex entries. So it would be maybe it would be a good questions to ask what is an example of a compact Einstein manifold that cannot be embedded in the projections of a matrix algebra, because you go very far, because you choose a very huge one-Newman algebra to embed Einstein manifold in them as a projection. So because the concept of the Einstein manifold is very subtle, providing examples of Einstein manifold is very difficult. So my question maybe for possible research is that what would be an example of a compact Einstein manifold that need really this huge embedding that cannot be embedded as projections of a matrix algebra, whose metrics comes from projections of from pullback of the metrics of the matrix algebra. Because I read in the book of Einstein manifold by Arthur, indicating that finding counterexample in the Einstein manifold theory is very difficult. He said that if you provide a non-trivial example of an Einstein manifold, I invite you for a dinner in a very luxury restaurant. I mean, yes.
So, Arthur best book, yes. I know it, and actually it's true. It's difficult to solve the Einstein equations on compact manifolds. Very likely on non-compact manifolds there is no obstacle, but in case of compact manifolds there are topological obstacles by Hitchin and others against solvability. But these are not sharp constraints. So yes, actually this is what I wanted to say, but finally I forgot that. Maybe use, and so now I characterize the Einstein equation as a sort of fixed point subalgebra of some dynamics on this Neumann algebra. And we always know that fixed point subalgebras are so-called, which come from a periodic inner automorphism, always are normal subalgebras of the type 2-1 factor. This is the theorem of Stirner from 1978. So I repeat again, so the fixed point subalgebra of a periodic inner automorphism of the type 2-1 factor is a normal subalgebra. And now, just to answer your question, maybe it would be interesting to see some sort of correspondence between four-dimensional Einstein manifolds and normal subalgebras of the type 2-1 factor. I think if it would be some sort of correspondence, it would be an interesting characterization about the solvability of the Einstein equation, because as a PDE, it is unmanageable typically.
And somehow it would substantiate your explanation about this symmetry breaking and emergence of...
Yes. Like basically, it would mean that we move from the original big type 2-1 factor to one of its normal subalgebra. But not every subalgebra of the type 2-1 is normal. So there are even, Neumann gave counterexamples, factors which are not normal. So the type 2-1 factor doesn't have the normality properties. Not every subalgebra is normal. So maybe in this way, the difficulty with the Einstein equation is transferred to the classification of normal subalgebras of the type 2-1 factor, because not automatically all of them normal. So, but I think this would be an interesting algebraic characterization.
Okay.
I don't know whether I'm allowed to ask one more question.
Oh, no, let's stop it now, because it's already like 1 hour discussion. So I think that's enough.
Okay.
But I am ready to continue it even in personal Zoom or something.
Yeah.
Okay, so maybe I would send you an email. Okay.
Yeah, yes, please. Thank you very much. Yes.
Okay, let us question our speaker again. Thank you.
Very interesting talk. Thank you.
Thank you very much.
Let me stop recording.